And I will make sure that I am muted. Hello, everyone. Hopefully this video works. I wanted to welcome you. We're going to talk about alkynes for this video. We're going to make two different videos on alkynes. For this one, we're going to talk a little bit about the acidity of the terminal hydrogen on an alkyne, as well as things like bromination and hydrogenation. After that, we're going to talk a little bit more about when we add OH, because that's a little bit different. So I wanted to get started. And we've talked about alkynes, and they're basically a souped up nucleophile, right? There's a lot of electron density. That's how you read these electron density maps. The more red you are, the more electron dense that area is. So you do have a good deal of electron density right here in the middle where that triple bond is. And it makes sense, right? There's a lot of electrons in that small space because that small space is sharing 6 electrons. So a lot of what I will also do is draw a comparison from alkyne and alkene, so that we're also bringing our understanding and a review of our alkenes. Okay, boom. So we talked about acidity of terminal alkynes, and we talked about how they're much more acidic than an alkane. So this we can actually deprotonate with a very strong base. These would not deprotonate with something like NaNH2. Let's go on. Why am I not moving? So I'm not gonna, so what it means, again, is, again, we need a strong base, and normally you guys go NaOH. NaOH is not a strong enough base. If you look on the bottom here, NaOH will not deprotonate because water is the stronger acid. So water will donate a hydrogen more readily than acetylene will. However, if we're using NaNH2, where we have the where ammonia would be our acid and its conjugate base here, this is a much weaker acid at 38 that can pull off this proton. So a lot of times I also call the alkyne chapter the NaNH2 chapter, because we do a lot to deprotonate it. It's also used to form alkynes, and we'll get into that in a moment too. Okay. So when we're talking about acidity and can we deprotonate, you need to be a stronger base than the acetylene hydrogen. So this is at around 25. So our acid, which means your acid has to be less strong, making your base more strong. So all of these that have pKa's higher, they are going to react with their conjugate base will be enough to deprotonate an alkyne, whereas all of these that are below, that are stronger acids when protonated, they will not, because they will protonate the alkyne. We're talking about being able to deprotonate here. That wasn't what I wanted to do. We're talking about being able to deprotonate here. And these are all strong enough to do it. These are not. So it's kind of that mixing, matching. You want to make sure that the acid that you're trying to deprotonate is weaker, is stronger than the acid of the conjugate base you're using to deprotonate, if that makes sense. Okay. Righty. Let's go back here. Let's talk about preparation of alkynes. Whoops. And like I said, we're going to be comparing alkynes to alkenes. So the only way we know how to make an alkene is through elimination. We're going to learn other ways later in Orgo 2, but for right now, it's elimination. And with elimination, you need a leaving group and a strong base, or a weak base if it's E1. For an alkyne, you have to do that twice. So you need 2 leaving groups and probably a stronger base. Because when you think about the mechanism, pulling the proton and getting that reaction from the alkene is going to take a stronger base than it initially did to do it a second time. There, here. So now we're going to move back and look here. And notice when we talk about our reaction, the first step is we do an E2 and we get our alkene intermediate right here. Then we do the reaction a second time to get our alkyne. Notice my bromines can be on the same carbon, that's geminal, or they could be on different carbons, but they have to be on adjacent carbons, and that's vicinal. If I have more than a carbon away, I can't make my alkyne. So they're either on the same carbon or on the carbon right next to them. So when we do this reaction, remember I said you need a really strong base, and I also said NaNH2 is kind of the code for, like, a lot of things are done with alkynes in this. So we already used this as a base to deprotonate the alkyne. Now we're going to use it as a base to form the alkyne. So as we mentioned earlier, this is a super strong base. Whoops, see, ammonia is its conjugate acid. So ammonia is kind of there being generated. We form our alkyne, and if we have excess Na sodium NaNH2, I could actually just get my alkynide ion, and I could immediately go into an SN2 reaction. If I don't want this, if I want my alkyne and I want to do something other than using it as a nucleophile, I need to provide aqueous workup, because I need to then protonate. This is if I want to go straight to substitution. This is if I want to do some sort of reaction a la alkenes, like adding a halogen or adding an alcohol or ozonolysis. Those are the type of things for this bottom one. So if I'm looking at this, what you can see is that when you're looking to see where the alkyne will form, I look at, okay, this is going to be my carbon that it's bound, where both the halogens are bound to. So the only alkyne I can form is going to be right here between these two carbons. Whoops, not that bigger. Control Z is right here. And it's just an elimination. Instead of just being a single elimination, it's a double elimination. So now we're going to talk about hydrogenating alkynes. They call it the reduction because as organic students, I'm going to give you a little definition for what we frequently in organic chemistry, we define reduction as adding hydrogen and we define oxidation as adding oxygen or removing hydrogen. And reduction would also be or removing oxygen. Okay. So that's kind of the way we're going to be going. Okay. So now, mousy. So when we're adding hydrogen, if you remember with an alkene, if I looked at this and let me draw the alkene that would be analogous to this, it would just be boom, boom. Doesn't really matter if I'm looking at a cis or a trans. Let's see. Let's do that. Whoops. And then here, if I add the hydrogen, I would get this product. So when I'm doing the same reaction with the alkyne, if I'm just adding hydrogen, it will first form the alkene. And remember, it's going to form that cis alkene. Then it's going to go on with more hydrogen because we can't use just 1-to-1 because you're basically saturating your flask with hydrogen. So here's my synthesis of my intermediate alkene. But by the time I get it out of the reaction, I have enough hydrogen palladium that I'm going to wind up with an alkane. So this hydrogen and platinum goes from alkyne to alkane. We're now going to add reagents that will allow us to stop during that reaction. So that we have different options. We don't have to go all the way to an alkane. So if I have something that stops at the alkene stage, that doesn't allow the reaction to proceed a second time, that will give me an alkene, and stereoselectively, since it's a syn addition, it will give me the cis alkene. So we call it a poison catalyst. It's basically adding it's a very similar reaction, but if you look at, we call it either a poison catalyst or we call it Lindlar's catalyst, which is shown down here, where basically this stops the reaction from reducing a second time. It stops the hydrogen from adding it a second time to the substrate. So you reduce to the alkene, then you're done. The catalyst quenches itself. Nice. And because it adds basically the same way that the normal hydrogenation is, it's going to add syn, and you're going to have a syn alkene. So when you look and you're adding hydrogen, right? Let's talk about energy. You have a catalyst that brings down that energy, because normally hydrogen just doesn't add to a double bond or a triple bond. So the catalyst brings down the energy for an alkyne, but it doesn't bring down the energy for an alkene. This also means that if you have a molecule with alkenes in it and an alkyne, and you want to selectively reduce the alkyne to an alkene, you can do that. If you are trying to get a trans alkene, you can't do that with that metal catalyst, because again, it works by the compound binding to the catalyst and then coming off. Boom, boom, off. So the way to do this stereoselectively is to use sodium and liquid ammonia. Please note, this is not the same as NaNH2 in ammonia. This is sodium and liquid ammonia. And I know they're very similar, but that I'm not going to go into the mechanism. It's stereoselective for the trans. I think there's a radical intermediate. I don't totally remember the mechanism, but it's a very different mechanism where you add one side and then the other side. And because trans intermediate is more stable, it's going to form the trans. So if you look with the alkyne, just by adding hydrogen, you can get 3 different products. If you want to have a cis alkene, you use H2 and Lindlar's catalyst. If you want to have just the alkane, you add H2 and platinum. If you want the trans alkene, you add your sodium and liquid ammonia. So you, from this one starting material, you can add hydrogen 3 different ways. Okay? And you can have 3 different products. Yay. Okay. So now I want to talk about hydrohalogenation to an alkene. So remember, sorry, an alkyne. So if you remember, this is the reaction we did with alkenes, right? We talked about how to do this. Addition to the alkene, blah, blah, blah. This goes Markovnikov. With an alkyne, we can do the same thing. But now, if I have excess amount of this, and if I have excess HX, I can just react and make, come on, and make this geminal dihalide, where I'm going to add the X to the same carbon due to Markovnikov's rule. Notice Markovnikov is basically probably going to work if you're allylic, benzylic, or terminal. Otherwise, they're going to be very similar in terms of those spots. So So this doesn't really add in that, making that carbocation, because carbocations on a double bond are not very stable. They're kind of trying to be linear and all sorts of things. So the mechanism is going to go by a slightly different mechanism. I have it here. Where it's going to be add the halogen, it may be that two different halogens add at the same time, like the hydrogen adds at one spot and the hydrogen adds at a different spot. So the mechanism is not the exact same mechanism. We're not really going to do the mechanism of this. In fact, I don't think we're doing showing many mechanisms for the alkynes, but what you can see, and again, this is a proposed mechanism, it's kind of what I was saying, is that there's two different acids. One is donating the hydrogen, the other is donating the halogen. So you almost have this like E2 reaction in reverse, where you're adding two different things at the same time. And then once you get to this product, that would then go by the traditional, make the carbocation and add to the most stable carbocation. So just like with alkenes, you can use peroxides. And I think it still only works with HBr. I don't think the peroxide works with anybody other than the HBr. Definitely not for alkynes. So if you wanted to do something like have a Cl, you'd have to do other reactions to get to that chlorine. Alrighty. So now we have, if I add XSHX, I can make a dihalide, a geminal dihalide, where they're on the same carbon. If I treat a dihalide with NaNH2 and ammonia and then work it up with water, I have an alkyne. And if it's not a terminal alkyne, I don't need to worry about that water step because I'm not deprotonating anything. See what other slides I have now. I'm going to stop the video here, and then we're going to talk about hydration, and then what's called hydration and adding the other reactions. So let's look here for a sec, because I'm making myself nauseous. We just during this video, we went over reactions 1 and 2. We went over reactions 1 and 2. We went over this one where we synthesize it. So that's all. So 1 and 2, hold on, shift C. So 2 and 3 are the same, right? One is adding excess, one is not, but they're both adding a halogen. These are both how you make the alkyne through elimination. And we went through all of these possibilities of adding to this alkyne. We talked a little bit about doing the substitution. We'll talk more about that later in the next lecture or something like that. But again, we now have to do this last set of reactions and also discuss alkynes as a nucleophile into my next video.